So here, these are the three criteria for three regions. You have cutoff region. When the cutoff will be there, the equation is IDS is equal to 0. Okay. When the cutoff is there, the equation is simply IDS is equal to 0. Okay. When the cutoff, when this is cutoff. When this is linear, your equation is this one. IDS is equal to beta VGS minus VT minus VDS by 2 into VDS. Okay. When you have a saturation region, your equation is like this. IDS is equal to beta VGS minus VT whole square divided by 2. Okay, got my point? Three equations for three regions. Now, when to use which formula? Okay, that is your concern. So I can give you some math, but I will not tell you which formula you have to find out or which region it is. Okay, so what you have to do, you have to find out the region where your NMOS is in right now. So how to do that? You have to use some condition. What are those conditions? Okay, let's see this condition. When your VGS is less than VT, when your VGS is less than VT, that is cutoff, or if that is bigger than VT but VDS is equal to 0, that time. That means if your VGS is less than VT or your VDS is equal to 0, that time what? That time it is cutoff. Your VGS is less than VT, it is cutoff. Your VDS is equal to 0, that is cutoff. Okay? Two conditions for this region. When your VGS is more than VT, but your VDS is more than 0, but less than VGS minus VT, that time it is linear. When your VT is less than VGS, that means your VGS is more, and your VDS is more than 0, but less than VGS minus VT, that time it is linear. And when your VGS is more than VT, and your VDS is equal to more than or equal VGS minus VT, that time it is saturation. Understood my point? When your VGS is less than VT, it is cut off. When your VDS is equal to 0, it is cut off. When it is opposite, that means like this actually, it is linear. Or linear has one more equation because it is and, not or. Remember, it is and. It cannot be 0. It is more than 0. So it is more than 0. And it cannot be greater than or equal VGS minus VT. So it should be less than VGS minus VT. Understood? That time it will be linear.
Yes.
So if it is more than VGS, if VGS is more than VT, but in this case, this is greater than or equal, that time it will be saturation. Okay? So three equations and few conditions. So you have to understand those conditions, then you have to apply the formula. Remember, there can be some Viva questions from there as well. Okay? Remember. So threshold voltage VT, we will derive this later. We do not need it right now. We will consider it as a constant up to this point. So when we will get time or when we will need it, we will derive it again. Okay? Until now, you should study up to these. Okay? We'll do that later, not now. Now we will go to the lab. We'll move towards the lab. Okay, this was our first lab. Remember, this was our first lab. This is for simple CMOS inverter. Today we will be doing a bigger circuit that is called CMOS NAND and CMOS NOR. I'm going to do CMOS NAND and you are going to do CMOS NOR. Okay?
Okay, sir.
Okay. So what are the objectives of our lab? To identify and mark different nodes of an Nand gate and a NOR gate, to create a circuit file, that means the coding, for Nand gate or NOR gate, to analyze the circuits using SPICE transient analysis capability, not DC, transient analysis. Because previously, remember I told you, your W is what? 12. Your L was what? 3, right? And your W was what for NMOS? 4. And L was what? 3. So your L are always same, okay? 1:1. The ratio of L will be same, 1:1, okay? Because 3:3, that means 1:1. But your W, what is the ratio of them?
3:1.
3:1. Remember this. So we will be using this 3:1 in our second lab as well. Your length will be same always, 1:1, but your W will change. Okay. And let's go back. Now CMOS NAND. This is our CMOS NAND. This is our NAND gate. Here we have to do the sizing first. Although we have written 2, 2, 2, 2, but this will not be 2, 2. This will be 2 for this lab, because we are actually considering 3:1, right? 3:1. WP by WN is 3:1, right?
Yes, sir.
Okay. What do I mean by these? I mean these. This thing you will not understand in one class. Remember, this thing you will not understand in one class. You need multiple classes and multiple topic to make you understand this. Okay? So do not expect this to understand in one class. This is 3, this is 1. Okay? 3:1. Or actually this was not 3, this was actually 12, right? And this was actually 4.
Yes.
We are not writing L, we are actually only writing width. This was 12:4, that means 3:1. So we can write 3:1. So if it is 3:1, this will be what? This will be 2, 2. And this will be 3, 3. How we got 3, 3 and 2, 2, we will explain later, not now. In our next theory class, that means maybe tomorrow, right? Tomorrow is our theory class. Hafiz, when is our next theory class?
Maybe Thursday, sir. Tuesday. Tuesday.
Which day?
Mongolbar, I think.
No, Mongolbar, I do not have any class, I believe.
I'm not sure. Let me check, sir.
Tomorrow. Tomorrow, Sunday. From 11 to tomorrow. Okay?
Yes,
tomorrow we will learn about CMOS design and CMOS sizing. Okay? CMOS design first, then CMOS sizing. Got my point?
Inshallah. Yes,
Inshallah.
okay.
And one more thing I need to, okay, let me. Can you see the screen? I need to pause the recording. Okay. So your 1 is equal to 4 micro, your 3 is equal to 12 micro, right? So
Yes,
your
sir.
2 is equal to 8 micro, your 2 is equal to 8 micro. Your 3 will be what? Again 12 micro.
12 macro.
12 micro. Now, this is very simple. You understand this thing very well. The only thing you didn't understand, I know that is how this thing has come, right? Why this is 3, 3? Why this is 2, 2? Why these are similar? These are similar, right? Why these are not similar? Got my point? Your PMOS was 3, our PMOS is also 3. Your PMOS was 1, but this time our our NMOS was 1, this time our NMOS is 2. Why there is a difference? We can do it when the time has come, okay? Right now, you just pretend you know it, okay? This is 3, that means 12. This is 3, this is 12. This is 2, this is 8. This is 2, this is 8. Okay, understood? Okay?
Okay, sir.
Okay, now we will go for the coding. Once it is done, we will go for the coding. So what was the code? I'm going to use the previous code that we have already done. Go to the desktop. What is the code? Where is the code? Maybe here, this one. Copy. The exact same code that we have already used in our what? In our previous class. This one. Exact same code. Just we'll just modify that. Okay. Now here, before going anywhere, let's write this again. This is 3. This is 2. Okay. Now, after we design, we size, then we what? We name. We will give some name. What are the names? I'm going to give the names. This is what? Let's say this is MP B. Why? Because it is connected to B, right? Let's
Yes.
write MPA. Why? Because this is MOSFET, this is P type, this is connected to A. That's why I have written this name. You can use your name as well. M1, M2, whatever you wish. This one is what? M, that is MOSFET. N, because this is N type, and it is connected to A, right? Like that. This is M, N, B, like that.
E.
Understood? Understood? Okay. Now I'm going to write the drain gate source. Which one is drain? Which one is gate? Which one is source? This one is what? Gate. Gate. This one is what? Source.
Source.
Source. This one is drain. Drain. The upper one is what? For NMOS is drain.
Drain.
This one is source.
Source.
This one is drain. This one is source. This one is gate. Gate. Okay. So our naming is complete. Okay. Oh, by the way, this one is called VA. This one is called VB because voltage are always started with V. This one is output. Now output should have a capacitor, not an LED, because you cannot use LED in the simulation. You have to use a capacitor. Understood?
Yes, sir.
Now this is CL, capacitor. CL. Okay. Now we need what? So after we design, we size, we name. Now we will give some node. We'll use some what? Some noding. We'll use some what? Noding, right? Now, at first, what node we have? We have a node here that is 0. Okay?
Yes, ground 0.
This is 0 node. This is also 0.
Yes.
Next what? Our
1.
input. Our input is 1. Which one is 1? The A is 1. So this part is 1.
Node.
This one is 1, right? Next what?
2.
Next one is 2, right?
Yes.
Let's say this is our 2. So this part is 2. This is also 2, right? Understood?
Yes, sir.
Now next what? We do not have any more input. So let's go to the VDD. Now VDD. This is 3. That means what? That means this part is connected to VDD, right? That means 3. Understood? Next what?
Yes,
what are the area that are left? This one is left, right? Okay. Let's use another color. Okay. Let's say this is our what? 4. Okay. I'm going to give a what? I'm going to give a circle so that you can understand this is our node. Because there are lots of numbers are there.
Yeah.
3. Okay. Then we have what? 4, right?
That's 4, yeah.
I'm going to see why is our 4. This is our 4. This is our 4. This is connected to 4. This is connected to 4. This is connected to 4. Right?
Yes, sir.
The whole thing is 4. Any more thing where our colors are not there? Anywhere? Yeah, we got one. This one.
Another
Another
green.
one.
Yes, sir.
This one. Okay, let's use another color. Let's use this color. Okay, let's write. What is the name? 5, right? This will be 5, and we are going to circle it. So we have 5 nodes. Understood? So now I'm going to convert this thing to what? I'm going to convert this thing to a design, to a what? To a code, right? So see, everyone. At first, how many MOSFET? P MOSFET I have. P MOSFET. How many P MOSFET I have? P MOSFET. P.
2.
2. It's MPB and MPA, right?
Yes, sir.
How many N MOSFET we have?
2.
2. So I'm going to copy this MPU. That means our P MOSFET twice. I'm going to copy this our N MOSFET twice. So first one will be called MPA. Second one will be called MPB. Third one will be called this one, MNA. Fourth one will be called MNB. So first one, that means which one? First one is which one?
First one is
MBA.
This is the MPA, right?
yes, sir.
Yes.
Okay. Where it is connected?
It's connected to the VDD.
No. Drain gate source body. Drain gate source body. What is the drain?
Drain will be 1.
No. Drain.
Drain will be drain 4.
4. 4. Then gate is 1.
Gate 1.
Source
Source 3.
3. Very good.
Hmm.
Source is 3, right? Body is also
Yes,
3.
sir.
Drain gate source body.
1.
So what is the sizing? What is the
One.
sizing? No. Sizing.
3.
3
Size
means
is
12.
3.
12, right?
12, yes.
12, yes.
Yes.
Now go to the next one. We do not need this anymore. Next one is this one. MPB, right?
Yes, sir.
So MPB, tell me. Drain,
Drain will be 4.
4.
4.
Then,
Gate will be
Be
1.
1.
no, gate will be what? It's
One.
gate.
1.
1 or 2?
2.
Source? Source?
2.
3.
Or
3.
Source
Three.
will be 3.
Body is also 3. And what is the sizing?
Yes.
Size is 12.
12.
12. Now see, these are P type. This is PENH, P type. Understood?
Yes, sir.
Yes, sir.
Okay. Now go to what?
MNA.
Type.
Okay.
NMA.
NMOS.
MNA.
MNA. This one.
Yes, sir.
Now again, drain gate source body. What is the drain?
4.
4. What is the gate?
Gate will be 1.
1. Source?
Source
5.
5.
5, sir.
And so body is also 5. It is N type. What is the sizing?
Sizing is 8.
4. 4.
8.
8.
It is
8,
2, so it will be 8. Okay. Next one?
Will be
MNB.
clear is 5.
5.
5.
5.
5.
2.
2.
5, 2,
0.
0, 0, right?
Yes, sir.
N type, and the sizing will be what?
8.
It is 2, 8. See, online class is not bad because in online we can actually use a lot of colors, right?
Yes, sir.
It's not that bad. So for all courses, it is not bad. Maybe for some courses it might be bad, but for not all courses. VLSI is a very online based. Okay, you can actually take a lot of online classes here. Okay, now the VDD. VDD is connected where?
Ground.
3.
No, VDD is connected to VDD is connected to 3 and the ground, right?
Yes.
3 are
So
ground. Yes.
we'll write 3 and ground. And what is the voltage? Is 5. Okay.
5.
Now, how many input we have? We have 2 input. One is VA, another one is VB. VA and VB. So VA is connected where?
Gate 1.
No. Number 1, right?
Yes,
Number 1, yeah.
Number 1. and VB is connected where?
Two.
Number 2. And the other pin is connected to ground. That's why it is written. This one is also pulse. This one is also pulse. Now here, I want you to understand one thing very clearly here. So if we give the VA and VB same. So now what will be the logic? This one is 0, 1, 0, 1, 0, 1, 0. This will be 1. This is also 0, 1, 0, 1, 0, 1, 0, 1. Now at a time, how many types of things you can see? Here you can see 0, 0. Here you can see 1, 1. Right?
1.
Here you can see 0, 0. Here you can see 1, 1. 0, 0, 1, 1. But can you see 0, 1 and 1, 0?
No.
No. So if your timings are same, that means here your timing is same. Your on time and off time timing are same. You can only see 0, 0 and 1, 1. You cannot see 0 and or 1, 0. So what are the things you have to do? You can do a very clever thing, that is doubling the time. If you double the time, so what will happen? See, this will happen. If you double the time, this is 0.
0.
This is 0. This is 1, 1, 0, 0, 1, 1. So what you can see now?
0, 0.
You can
1,
see 0, 0.
1, 0.
You can see 1, 0. You can see 0, 1. You can see 1, 1. Right? This is a very clever thing we have to do. That is doubling the time. We will double the time of 1. So this is 0, 5, 0 volt, 5 volt. 0.3 is the delay time, rise time, fall time, on time, and total time, right? So we will double the time. What time? This time, no. We do not have to double the rise time and fall time. We only double the period and the total time. Okay, we'll double the time so that we can see both, all of them. Okay, now this model specification will remain as constant because actually we are using the same material for all our design. That's why the 3:1 is constant, 3:1. Now the capacitor, our capacitor is connected where? This was okay. We somehow we delete that. This was our what?
4.
Yes.
Capacitor was 4.
Yeah. So we will give 4, and it will be 50 picofarad, femtofarad. Sorry, not pico, femtofarad. And our transient analysis will be 1 nanosecond, and highest it will be 80. Now, what is our highest time?
80.
So it should be at least 80. It is less than 80, we cannot see all. We have to at least see 80. So this one and this one should be matched, okay? Or I should say this one should be bigger than that. If this is 80, it should be 80 or more than 80. Now DC analysis we do not need. We'll delete that. Because the only purpose of the DC analysis was to find it is 3:1, right? In previous lab, we have changed the values and we agree it will be 12:4. That means 3:1. That was the purpose of DC analysis, and the purpose is already done. So we already used 3:1 here, right? We already used 3:1 here. Remember? According to the 3:1, we use 3 and 2, 2, right?
2, 2. Yes.
According to that, we use that. So DC analysis, we no longer read. Now then dot probe dot end. Now what? After we make the code, now what? Remember, go to the file, save as. What do you write? CMOS NAND, N-A-N-D, NAND.
CMOS.
Dot
Yes.
CIR. Remember dot CIR? This is a very important thing. You have to rename CMOS NAND dot CIR. Dot CIR is very important. That means that is a circuit file. And you have to choose the type to file, all file. If you do not choose the all file, you will not get the what? Not get the circuit file. Understood?
Yes, sir.
Okay, save. Okay, let's see. Here, can you see it is a CMOS NAND? If you double click it, your software will be open. Now run. Run. Oh no, go to the trace. Here we need what? We need CL, we need VA, we need VB. Okay, all the V means voltage. Voltage CL, voltage VA, voltage VB. Okay, if we click OK, this is our answer. Now this one, that is our output. The red one, is our VA. This blue one, can you see the blue one, or I should say change the color? The tail color. Is our VB. Okay?
Yes, sir.
So what is that? Okay, I'm going to make it even bigger. So what is happening here? Your A, here the A is 1, here A is 0, here A is 1, here A is 0. Okay? Got my point? Your
Yes.
B is 1, B. Here B is 1, here B is 0. How do I know that? Because it is at the ground, right? Here, can you see the teal color? It is 0.
0.
0. What about your output? Your output is 0 here. Your output is 1,
1,
1,
1,
1.
1.
So that is your NAND gate, right? Your NAND gate 0, 0 is 1, 0, 1 is 1, 1, 0 is 1, 1, 1 is 0, right? So your NAND gate is okay?
Yes, sir.
Okay. So your NAND gate is okay. So your performance analysis is done. Now I want you to make the NOR gate. Okay. So I'm going to show you the design. Oh, no, not. Okay. I'm going to draw the design, and you write the code. Okay. Can you do that?
As homework.
No. Now.
I will try.
Okay. I'm going to. Okay. You try. Okay. No problem. Do not worry. You try. I'm going to write. I'm going to do the design for NOR gate. You draw this design at your notebook. This is your A. This is your B. That means this is also A. That means these are actually connected together. Okay, I'm writing them separately. You can connect them together, but that will make your design more more complicated, right? This is B. This is VDD, and this is your output. That is your Y. Okay. Now, what you have to do? We have to write the sizing. Here the sizing will be 6, not 3. Here the sizing will be 1, not 2. 3:1, right? Because they are double in the series line. That's why the 3 will be double. And here they are 1 single in the one line, one series line. That's why they will be 1 time. 3:1 be 6, 6, 1, 1. You will understand it more later, not now. So the sizing is already there. And here you have to use a capacitor as your output. So can you write the code and do the sizing?
Yes, sir. We will try.
You try, okay? I'm going to show you the coding as well. Wait a second. Wait a second. Okay. Now take 10 minutes and do it, okay? I'm going to pause the recording. This is for NOR gate actually. So 2 input NOR gate. So I have given the noding. So this is 1, this is 1, this is 2, this is 2, this is 3. That is the VDD. This part is called is 4. This whole part is 5. That is this purple, not the violet color, right? The purple color is 5. Any more? Do you have any more? Any more? Nothing, right?
Yes, sir.
Okay. Now we can start writing. So MPU again, copy, because this is PMOS, NMOS, MPA, MPB, MNA, MNB, right?
Yes, sir.
P type, F. Okay, now the sizing. At first, fix the sizing. This is 6, right?
Yes.
6 means what?
24.
24. Next one is also 6, it is also 24. Next
12.
one is 1 and 1,
Four, sir.
4, 4. Okay. Now the numbering. Okay. So this one, A, drain, gate, source, body. What is the drain?
4.
4. Gate is 1. Source is
One.
what?
3.
3. Next one. Next one is what?
Drain
Three.
is 5,
Yeah. 5,
2,
2,
4,
4, 4.
again 4.
Okay. Next one is MNA. This one. Drain, gate, source, body. What is the drain? Drain is 5, right?
Drain
Five.
is 5,
5,
5,
1,
1,
0.
0, 0.
0.
Next one. This one.
MNB.
Drain is 5,
5,
5,
Okay.
1,
2,
2, 2,
0, 0.
0, 0. Okay. Now the VDD. VDD will be what? 305, right?
B 3 0.
3,
05. Now
5.
VA, copy, paste, right? First one will be called VA, next one will be called VB. Where is VA connected? Number 1. Where is VB connected?
number 2.
Number 2. Now the sizing and the numbering will be what? Double. I told you before, right?
Yeah.
Okay. Now where is the capacitor connected?
5,
5.
Capacitor 5.
PC analysis you do not need. Okay, done. Now I'm going to write what? I'm going to save as for the desktop as CMOS what? NOR, right?
Yes.
Dot CIR, right? TXT will be all file. Save. Understood? Everyone?
Yes,
Okay.
sir.
Now I do not need these whiteboard anymore. I'm going to click these. Okay, that is the CMOS NOR. I do not need these. I'm going to close it. Okay, this one. This is the code that we have written, right?
mm,
Okay, I'm going to write it. I'm going to run it
trace,
here. Now at trace
VA, VB, VCL.
VCL VA VB, right?
Yes, sir.
This green color is our what? Is our output. So if we can actually make the red one bigger. This one is our 1. That is A. Okay, I'm going to write. See, your A is 1,
1
0, 1,
1
0. Your B is 1, 1, 0,
0.
0. And what about your output?
0, 0, high.
0, 0, and high, right? 1.
1.
So see about the NOR gate. For 0, 0, it is 1. For 0, 1, it is 0. For 1, 0, it is 0. For 1, 1, it is 0. So our
Yeah.
truth table is correct, right?
Perfect, perfect.
Perfect. This is
Exactly.
how you can. This is how you can what? You can actually do the simulation. Now today's work, you have to do it at your home, okay? And next class, in the next class, that means when? In the
Next
Saturday.
Saturday.
Saturday, you have to submit what? You have to submit 2 things. One, all of you have computer, right? I know it.
Yes, sir. Most.
What you have to do, you have to submit me this coding and this result. Okay?
अच्छा
And one more thing, and you have to submit, and you have to do what? You have to give me that diagram that we have drawn, right? Okay, you can say,
not diagram.
yeah, diagram is also necessary, because how do I know your noding is correct?
Yeah.
Okay, how you can write the noding? You can write in the what is that? You can write in the Zoom as well. You click the Zoom, go to the screen share, whiteboard, share. You can see this, right? And from here you can take a screenshot. There is a button. There is a button called screenshot. If you click it, not that. Not that. There is a button called screenshot here. Here, save. Can you see that? You cannot see it, but I can see it. There is a button called save. If you click this, it will be saved in the where go to the document, go to the Zoom, the D26 lab. Can you see that? Can you see the screen?
We see white
Yes, sir.
screen.
Can you see this?
No, sir. Yeah,
Yes,
yeah.
sir.
26. If I go to that, because I clicked one save button, so that's why they will be here, like this. Okay, they will be saved as an image. You can draw these image by using Zoom, no problem. Or if you want to use this, you can use Paint. Can you see this Paint?
Yeah.
Yes, sir.
Go there, select this, and you can write like this using mouse. You can use different color as well. You can use brush. You can use something else as well, like this. Okay,
Okay, sir.
like this as well. You can do it if you want. You can change the brush. You can do it like this. Brush. Okay, you can do this if you want. This is not 100% mandatory how you do it, but I need three things: one circuit, one code, and one what?
Diagram.
This is screenshot. Take a screenshot and submit. Okay, this will be your first task, first job. In the next lab, you will be doing this. Remember, this job will be assessed. I will keep track. Okay, you submit one track, you submit one job. So, is this too hard for you?
No,
Yeah.
sir. No.
No, sir.
So, is this fine with you?
Yeah.
Because I want you to learn more, right?
Yes, sir.
Only giving you the lecture and only taking you the exam will not teach you the VLSI. Remember, VLSI is not that easy. Okay?
Okay, sir.
And I think it is fun. If you do it, you do it, right? And tell everyone else that there is a job. And all the jobs, that means all the labs and all the assignments, this is not assignment actually, this is actually homework. All the homework will be assessed. I will keep track of all homework, that you have done it, you haven't done it. Okay, I will give tick. All those tick will affect your grade. Okay? Anything else? Anything else? If you have any problem with my assessment, or if you have any problem with my teaching, you can tell me. You can tell me directly.
No, sir. No problem.
No
We
problem.
understood.
So I am the one who will know this one first. Okay, remember.